from today. So YOOJEONG already published a paper early this year. So we wanted to present her the papers based on the titles, hydrogen storage selection for Saudi Arabia, a multi-criteria decision-making approach under the interval value Pythagorean fuzzy environment. So let's welcome her with your great heart. Thank you.
Thank you. Good morning, everyone. Thank you for joining us today. To introduce myself, my name is YOOJEONG Oh, a master's student in Fahd in chemical engineering in Fahd University of Petroleum and Mineral. I am happy to be the first speaker in our research group's webinar session. And today I'll be presenting my research on hydrogen storage selection for Saudi Arabia, a multi-criteria decision-making under interval-valued Pythagorean fuzzy environment. These are the contents for today's presentation. Globally, there is a growing shift toward renewable energy sources to achieve a sustainable, low-carbon future, with hydrogen emerging as a key energy carrier. In line with this trend, Saudi Arabia is strategically moving toward a hydrogen-centric future. The country has set ambitious target to increase its share of renewable sources up to 50% by 2030 and capturing 10% of global hydrogen demand by 2030. Especially hydrogen is gaining significant attention due to its exceptionally high gravimetric energy density. However, its unique properties such as very low volumetric energy density and low ignition energy also present some various potential hazards. Therefore, adopting reliable hydrogen storage method is crucial to ensure the safe, widespread use of hydrogen. Selecting hydrogen storage technology is a complex decision-making problem for several reasons. First, it involves multiple conflicting objectives, not just economic factors, but also technological, social, and some safety consideration. Additionally, because hydrogen technology is still evolving rapidly, decisions cannot be solely relying on quantitative data, and it must incorporate some expert insights, which often involve subjectivity and uncertainty. Moreover, infrastructure development must align with regional conditions. And in this response to this need, in this research, we developed a comprehensive decision-making framework for hydrogen storage selection under uncertainty. Then we applied this framework to conduct a case study in Saudi Arabia's context based on the input from regional experts. To capture the uncertainty inherent in regional experts' opinion, we adopted a fuzzy approach, which will be further explained in this section. To recall you the definition of a classical crib set, in a crib set, an element is either belong to the set or it does not. So it's basically a binary representation. When a membership of an element is clearly defined, it can be represented by a classical crib set, such as determining whether a cup contains water or not. But when assessing whether water is hot, it's not just a simple yes or no answer, whether it can be totally hot, a little hot, or not hot at all, which means the different degree of the belonging. And by allowing this partial inclusion, fuzzy sets can mathematically express this degree of membership. Over time, fuzzy theory has expanded to broaden the domain that this degree can capture. In classical fuzzy sets, we define the degree of membership mu. Then the degree of non-membership is simply derived as 1 minus degree of membership. However, in intuitionistic fuzzy set, it introduces an independent degree of non-membership, thereby defining a degree of hesitancy, representing the uncertainty or lack of knowledge under the constraints that the sum of the degree of membership and non-membership is less or equal to 1. Further, Pythagorean fuzzy set further expanded this concept by relaxing this constraint, allowing the sum of the square of the membership and the non-membership degree to be less than or equal to 1. As we can see from the graph below, loosening these constraints allow us to represent a greater number of situations, providing a greater flexibility and an improved ability to handle more complex real-life scenarios using Pythagorean fuzzy method. Pythagorean fuzzy methods are particularly useful when both positive and negative attributes strongly coexist. Like, for example, when evaluating a political candidate, both trustworthiness and untrustworthiness, represented by the degree of membership and non-membership respectively, can be significantly high. So it could potentially exceeding a total of 1. In this case, intuitionistic fuzzy sets may fall short due to their strict constraints, whereas Pythagorean fuzzy set can, with their broader domain. Therefore, in this study, we adopted interval valued Pythagorean fuzzy sets, IBPF for short, collected experts' opinion using 10 linguistic variables through survey, and translated them into the corresponding fuzzy variables. Next is methodology. Our proposed methodology consists of 4 key steps: defining the problem, determining the relative importance of criteria, ranking the alternative, and conducting sensitivity analysis. As mentioned earlier, to ensure that our findings are tailored to the Saudi Arabia's context, we incorporated 8 experts from individuals with extensive knowledge of the Saudi Arabia's hydrogen landscape, ranging from industry, academia, and to research institutes. Especially, we use experts' input in the steps colored in blue to ensure that our problem formulation accurately reflects the real-world problem of Saudi Arabia, and as an input to assess both criteria weights and to rank the alternative. In the first stage, we established a hierarchical framework for the problem by clearly defining what to determine, what factors to be considered, and what choices are available in terms of objective, criteria, and alternatives. In the second stage, we determined the relative importance of each criteria used through AHP. Based on experts' pairwise comparison metrics using linguistic variable, we converted them into numerical values by defuzzifying them according to the IBPF sets corresponding to each linguistic variable. Then we assessed consistency, excluding one input with a consistency ratio below 0.1. Then finally, we normalized the metrics to derive the final weights for the main and sub criteria. In the third stage, we rank alternatives using Topsis method. Experts evaluated its alternative against different criteria through survey, and the response were converted into numerical decision metrics, aggregating 7 inputs into a single final matrix. We then calculated each alternative's distance from the positive ideal solution and negative ideal solution, and combine them into a single distance using weighted average from stage 2 and determine the relative closeness coefficients, RCC, for each alternative, and rank the one with the highest RCC as the most desirable option. Finally, in the fourth stage, we conduct a sensitivity analysis by adjusting the criteria weights. First, we interchange the weight of main criteria and examine the impact on the results. We identified one criterion significantly influenced the final ranking, and to further analyze its impact, we modified its weight while distributing the change equally among the other criteria. So now let's move on to the case study. Here we developed a hierarchical framework to determine the most suitable hydrogen storage option for Saudi Arabia. Our focus was specifically on selecting stationary bulk storage system rather than a vehicle-based or small-scale stationary storage, as Saudi Arabia is primarily focused on hydrogen exports, and there is currently no substantial domestic utilization facility to justify internal demand yet. Our evaluation considered four main criteria: technological, economic, social, and safety, along with 13 sub-criteria. 5 storage alternatives were analyzed: compressed gas, liquefied hydrogen, cryocompressed hydrogen, underground storage, and chemical storage. As results, the final weights show that decision makers consider economic criteria as the highest priority, followed by the technological factor. Among various sub-criteria, infrastructure-related criteria such as capex and infrastructure compatibility and domestic compatibility emerged as the most important. And as a result of ranking, underground storage stand out as the most suitable hydrogen bulk storage system for Saudi Arabia, followed by compressed gas and liquefied hydrogen. This table shows the result of evaluation where darker shades indicate more favorable performance. Based on the evaluation, underground storage achieved relatively high score in critical technological criteria such as storage capacity and life cycle, as well as in economic criteria such as OPEX, infrastructure compatibility, and domestic technological ability, all of which hold significant weights in decision-making process. Meanwhile, chemical storage received notable score, particularly in safety and social criteria, suggesting its strong potential as inherently safer system. For our sensitivity analysis, as mentioned earlier, we created 6 different scenarios by interchanging the weight of main criteria. And unlike the initial results in the previous slide, chemical storage rank as the most favorable in scenario 4 and 5, where the weight of economic criterion was swapped with social and safety criteria, respectively. This result indicates that chemical storage preference is highly related to the economic factors, becoming more favorable when economic considerations are less dominant. And for further investigation, focused sensitivity analysis was performed on the economic factor. As the change of economic criterion weights, underground storage, colored in brown, consistently hold its top position across the most scenario, indicating its resilience under the diverse economic priority. In contrast, chemical storage, which is colored in red, was highly sensitive to economic weight changes, highlighting its cost-related limitation for large-scale application. This suggests that if economic consideration become less critical, such as in scenario where safety take priority, or if chemical storage improves its cost efficiency, its inherently safety advantage could make it a competitive option in distant future. Next, let's move on to conclusion. So to sum up, in this study, we propose comprehensive multi-criteria decision-making framework integrating interval value of Pythagorean fuzzy with two pre-existing decision-making method, AHP and TOPSIS. The result of the case study highlight that underground storage is identified as the optimal solution due to high storage capacity, long life cycle, and economic benefits, aligning with Saudi Arabia's geological advantage. Meanwhile, chemical storage emerged as a competitive alternative when social and safety considerations are prioritized. For future studies, the criteria can be expanded and dynamic weighting mechanism can be incorporated to reflect evolving technology and market condition. In addition, comparative analysis across different regions or countries can be conducted. So these are the references for today's presentation. And for further details of this research, please refer to our publication in the International Journal of Hydrogen Energy published earlier this year. And you guys are also welcome to contact me via the email address shown here. And thank you for your attention.
Great. Thank you so much for your effort. Yes. So
Thank you.
really thank you. Yeah, I know you are the first presenter of our webinar, and then it was not easy to prepare it in a very short time, but your presentation was so meaningful for us. So Asmaila or Junso, do you have any question for her or any comment?
Oh, thank you for nice presentation. And I have one question in 27 in page 27. Could you move the slide in 27? Yeah. In this page, so underground storage has been selected as a suitable case, but actually I'm not familiar with the underground storage. So could you explain what underground storage is and why underground storage is beneficial in Saudi Arabia?
Thank you for the question. Actually, I didn't prepare appendix for today's presentation, so I can just explain. For underground storage, we compressed hydrogen into a compressed gas form and inserted into preformed geological formations such as salt carbon. And especially in our results, underground storage technology got high mark in some technological and economic criteria, which is related with infrastructure. This is because of Saudi Arabia's abundant geological formation, including salt carbon, and which are like already used as a storage for another type of gas.
Thank you.
Thank you.
Anything else?
Thank you for the very nice presentation. Yeah, so I have a little question surrounding safety and social impact. So from your analysis, we could see that in terms of safety and social impact, the chemical storage is more preferable than the underground storage. So if I was to place my priority more on safety and social impact, do you think there are factors that we could consider to make chemical storage more economically viable than the underground storage?
First of all, thank you for the question. And yes, actually, one of the main highlights of our results is that once we focus on the scenario with higher priority in safety and social aspects, then chemical storage turned out to be the most desirable option. And since our decision-making framework based on the combination of 4 different criteria, including economic, technology, social, and safety area, it doesn't necessarily mean that chemical storage option become more economical, but we can say that it become more desirable.
Also, Yoo-jeong, I have one.
Thank you very much.
Yeah, thank you. Yeah, I have one question. I think we already discussed several times, but just in your current view, what is the major limitations of your the previous research?
Limitation. In addition to what I already mentioned in the last slide for our future research, I think one of the limitation is rebuild when we first set the problem in our first stage of the methodology. Here we try to structure 4 different criteria, like 13 different sub-criteria under 4 main factors. However, somehow each sub-criteria, we can say each sub-criteria are related. So probably in our future research, we can clearly analyze the correlation of these different sub-criteria and reflect to our results.
Just I wanted to add one more things because I'm the author of this research. Also, I also involved in taking the survey as well. So one thing I noticed from this journey is that the export in Saudi Arabia, especially in terms of hydrogen, they are very specialized in technical and research, but not too much about process safety. So I feel sometimes they miss kind of safety concern compared to the other aspects. So I feel like in the future, if it's possible, we can reconcile the safety aspect with other aspect together. So I hope you can be the leader of this research. So yeah, this is what I wanted to share with you as well.
I see. Thank you for your idea.
Thank you. Yeah, so I think that's all. And then thank you so much, Yoo-jeong, again for the excellent presentation, and then and even the others for your active participations. So again, so we can just conclude today's seminars. Thank you.
Thank you.
Thank you so much.
Thank you.
Thank you.